Hello, a great welcome to this presentation. In this video, I will demonstrate the column base plate design using the Euro codes. Myself is Jarajan P. As you can see here on the side, I have provided you a three-dimensional sketch of a column base. Obviously, as you can see that it consists of a column that is welded to a base plate element, and you can see that on the corners you have the anchor bolts that is connected to the concrete block. Now, before getting into the details, I would like to list the documents that are used for the preparation of this design calculation. So essentially we have three documents. The first one is EN 199211, that is Eurocode 2, popularly it is known as EC2, and the title is Design of Concrete Structures, Part 1 of 1, General Rules and Rules for Buildings. So this is essentially a code for the concrete structures. And next one is EN 199311, that is Eurocode 3, Design of Steel Structures, Part 1 of 1, General Rules and Rules for Buildings. And coming to the third one, you can see that this is a very important document, very specific to the design of joints. And that is EN 199318, Eurocode 3 again, Design of Steel Structures, Part 1 of 8, Design of Joints. So I have used altogether 3 Euro codes for the preparation of this design. Okay, fine. Coming to the example problem, as you can see that I have provided you the detailed sketch of the plan as well as the cross section of the base plate. You can see that the total dimension of the base plate is 450 by 350, and we have provided a total of 6 anchor bolts, and the anchor bolts are positioned at 350 mm center to center in one direction and 250 mm in the other direction. And as you can see that an edge distance of 50 mm is used. And the base plate that is considered supports a European cross section, that is HE260A. And on the side you can see a typical cross section of the base plate. P and M are the axial loads as well as the bending moments acting on the column. And as you can see that the internal forces are clearly marked over here. That is one tension T, that's the total tension in the anchor bolts. Obviously, for this example, as the moment is applied in the clockwise direction, we expect the tension on the left side anchor bolts. And then we have the total compression C in the concrete, and that is distributed over a width known as the bearing width. And as you can see that E is the edge distance, and set T and set C are the locations of the resultant tension and the resultant compression measured from the center line of the column. One important aspect in the base plate design is writing correctly the equations of equilibrium. So for this base plate, we have essentially 2 equations of equilibrium. For example, if you consider the force equilibrium, sigma V equal to 0 will provide you minus T minus P plus C equal to 0. As you can see that all the loads are correctly marked on this sketch. And another equation is, we call it as the moment equilibrium. It does mean that the algebraic sum of the moments of all the forces acting about any point should be equal to 0. So if you look into this moment equation, you can see that the compression C is missing. This means that I have taken the moment of all the forces about the resultant compression C, I got the sum and then equate to 0. For example, you can see that the moment produced by T is T into set T plus set C, and the moment that is produced by P is P into set C, and then we have got a minus M. So on adding all these terms equating to 0, we have the moment equilibrium equation. So one should give a proper attention in writing these 2 equations very clearly. Obviously, before starting our calculations, we need to finalize the important parameters. This could be the geometrical parameters, this could be the material properties, or any other miscellaneous details. So now first let me start with the base plate dimensions. As I have already shown, the width of the base plate is 350 mm and its height is 450 mm, and the thickness of the base plate I started with 25 mm. And as already explained, the base plate supports a steel column a T260A, which is essentially a European cross section, and BC 260 mm, that is nothing but it's the width of the flange, and HC equal to 250 mm. This is the depth of the cross section, and TF, this is the thickness of the column flange, that is 12.5 mm, and TW, that is the web thickness 7.5 mm. And to help you out, I have written here, you can take all these dimensions from a standard handbook on Eurosection properties. Now coming to the concrete pedestal dimensions, I considered an offset of 75 mm all around the base plate, which means that I have got a concrete pedestal dimension of 600 by 500 mm. Now the next one is the important, that's the anchor bolts. We started with a diameter of 24 mm. The location details, as I have already shown, the edge distance is 50 mm, and in one direction the anchor bolts are placed at 350 and in the other direction 250 mm. Now is the tensile stress area of bolt, and I have found that people always get it confused with the gross area. And to help you out, I have written a very important note over here. To calculate the tensile stress area, please refer to table 4 of ISO 8981. And note that this is not the gross area, this is a reduced cross-section area inside the threaded part of the bolt. Okay, let us continue the input parameters. Now is the material. I have assumed a concrete grade of C2025 for my concrete pedestal, for which, as per the code, the characteristic cylinder strength FCK will be 20 MPa, and the long-term effect coefficient alpha CC is equal to 1. This is to be taken as per clause 3.1.6 of EC2. Then I presume that you have some basic understanding of the partial safety factors also. So the partial safety factor for concrete gamma C is taken as 1.5. You can directly have it from table 2.1n of EC2. Then there is a foundation joint material coefficient beta J, that is taken as 2 by 3rd, which essentially depends on the grout thickness as well as the grout strength also. And this shall be taken as per the clause 6257 of EC318. Then we have the base plate material grade, for which I assumed S355 grade steel, and I have it as the yield strength F5 for the base plate as 355 MPa, and this shall be taken as per table 3.1 of EC311. Now I have used class 8.8 anchor bolts, for which the ultimate tensile strength FUB will be 800 MPa, and this shall be taken as per table 3.1 of EC318. Now there is a factor, K2 factor for bolts, that is taken as K2 equal to 0. 0.9. This depends on whether it's a countersunk or other type of bolt variety, and that is taken as per table 3.4 of EC318. Then finally, we have the partial factors, which is detailed in Eurocode EC3, that is gamma M0 1.0 and gamma 2 1.25. This is gamma 0 and gamma 2 definitions are clearly given in the code. So I have, to help you out, I have written clearly here clause 6.1 of EC3 1 of 1 and table 2.1 of EC3 1 of 8 will provide you the guidance over these partial factors. Now coming to the applied load, we shall design our base plate for an axial load P equal to 400 kilonewton and M equal to 150 kilonewton meter. And here, as you can see, I have not reported any shear values, because in this calculation I presume that the base plate shall be provided with a shear key that is welded to the underside of base plate, and this shear key will take 100% of the applied shear, and the bolts will not be subjected to any kind of shear loads. Suppose this shear key is not provided. In this case, you have two mechanisms to resist the shear. One is through the joint friction between the grout and the underside of the base plate, or you can get it resisted directly through the anchor bolts. In case you make use of the anchor bolts, while checking the anchor bolts, it is important that you consider a proper interaction between the shear as well as the tensile loads. Okay, fine. So let us start solving this problem. The problem will be solved in different steps. So let us start with step 1, which essentially involves computation of internal forces. As already discussed, we have two equations of equilibrium as written over here through equations 1 and 2. that is sigma m equal to 0 and sigma v equal to 0. And before applying these equations, you would like to get the locations of the resultant tension set T and set C through this formula, which is very simple. And the values of set T and set C are reported over here. Now, as you can see that equation 1 can be rewritten as T, that is the total tension in the anchor bolts, is M divided by ZT plus ZC minus P into ZC divided by ZT plus ZC. And this equation will directly provide you the total tension in anchor bolts for an applied moment M as well as an axial. So for this problem, if you substitute the values of MP, ZT and ZC, we obtain the total tension in the anchor bolts T as 348.9 kilonewton. Please remember that T is the total tension, and in this case, it shall be shared equally by 3 anchor bolts. Now coming to the total compression in concrete bearing below the compression column flange, we can use equation 2, wherein we can write C equal to P plus T. We know the value of P, we just now computed capital T, so we can obtain the total compression C. So for this problem, we calculate the total compression C as 748 kilonewton. Please remember we are using the kilonewtons for the force. So the next step would be the computation of the design bearing strength of joint and additional bearing width. As you can see that in order to easily guide you for this calculation, I have provided 2 sketches. One is for the computation of the design bearing strength of the concrete, and the second sketch would provide you how the bearing stress is distributed over the width of the column base plate. Now as you can see that this particular sketch is nothing but, if you go back, so if you take a cross section across this compression flange, okay, means that you will have a width of the base plate C on one side, and also you have got another width C on the right side, and this cross section is what is shown over this sketch. Okay, so please remember, instead of the thickness of the web, it will be the thickness of the flange, and C is nothing but it is the width over which the bearing stress is distributed on each side of this compression flange. And remember that these sketches are obtained based on clause 6.7 of EC211. And here as you can see that in order to compute this design bearing strength, a frustum action is considered. And here as you can see, 2 areas are marked. One is AC0, that is nothing but B1 into D1, and this is what normally we call it as the bearing area at the base plate level. Okay, and you can see that there is a frustum action, and we obtain a design distribution area with the dimensions of B2 and D2, and B2 multiplied by D2 will provide you another frustum base area, that is AC1, and EC2 provides some restriction over D2 and B2, that is B2 should be less than or equal to 3B1 and D2 should be less than or equal to 3D1. Now first we proceed for the computation of the design compressive strength. This is done using equation 315 of EC2, wherein FCD, that is the design compressive strength, is calculated as alpha Cc into FCk by gamma c. Substituting the various values, we obtain FCD as 13.33 MPa. Now let us proceed for the calculation of the bearing width of the base plate T stub. Please remember that the computation of the value of C, it is basically a trial and error process. So to begin with, we start with the width of the bearing area C as 65 mm. Based on this value of C, we calculate the critical areas, that is the loaded area AC0, which is at the base plate level, and we also proceed for the calculation of the effective design distribution area AC1. So obviously we know that the effective width B1 of the loaded area is the thickness of the flange plus 2C, because as I already told you, the width C is distributed on each side of the flange. So which means that B1 will be 142.5 mm. Now the effective the base plate, obviously this is nothing but the width of the base plate, and that is equal to 350 mm. Now for the computation of the effective width B2 and D2, we need to think over how much the pedestal is extended beyond the edge of the base plate. So in this case, we can say that B2 can be computed as B1 plus 2 into 110 mm. Remember, this 110 mm is the 35 mm portion of the base plate and the offset 75 mm. Okay, and accordingly we compute B2 as 362.5 mm, and this is obviously less than 3B1. And the effective depth D2 will be BP plus 2 into 75 mm, where 75, as you know, it is nothing but is the offset from the base plate edge to the pedestal edge. So accordingly we obtain D2 is equal to 500 mm, and this is less than 3D1. So having calculated B1 D1, B2 D2, we can readily go for computation of the loaded area AC0, that is B1 into D1, and we can also calculate the design distribution area AC1, that is B2 into D2, and it is computed AC1 and AC0 over here. Now having computed AC0 and AC1, we can obtain the concentrated resistance force from the consideration of concrete strength. What does it mean? This means that how much concentrated force the concrete can resist, because we know that on the compression side of the bearing area, we have got a large compression acting in the concrete. So we need to check whether the concrete is safe. So we compute here the design concentrated resistance as AC0 into FCD square root of AC1 by AC0. Obviously, you know that AC0 multiplied by FCD directly provide you the area multiplied by the design bearing strength. And this simple resistance need to be multiplied by a factor square root of AC1 by AC0, which is obviously greater than 1, and this is on account of the frustum action in concrete under a vertical force. So accordingly, we calculate FRDU as 1.268 into 10 raised to 3, that is 1268 kilonewton. And remember, this formula corresponds to equation 663 of EC211. Now, having obtained the design bearing resistance, let us see what would be the design bearing strength of the joint. And this needs to be calculated as per equation 6.6 of EC318. And we obtain FJD, that is the design bearing strength, as beta J into FRDU by AC0. As you can see that FRDU is the concrete bearing resistance in compression. This divided by AC0 is the bearing area. So this is indirectly is the bearing strength at the concrete interface. This we reduce by multiplying by a factor beta J, which is nothing but it is a joint efficiency factor. So that is equal to FJD 16.945 MPa. Having calculated the design bearing strength, we can readily go for the computation of the additional bearing width, that is the actual bearing width C, based on the above value of FJD. And this is obtained using the formula CF is equal to TP into square root of Fy divided by 3 into FJD into gamma MO. And we obtain CF is equal to 66065 mm. And this formula we can obtain directly from equation 6.5 of EC318. Now what does this formula provide you? This formula simply tells you, in order to transmit a bearing stress which is equal to FJD without exceeding the yield stress of the base plate, what must be the allowable width? Okay, additional bearing width, that is a CF. So this CF is computed based on a limiting yield stress in the base plate and a limiting bearing strength in concrete. So CF is equal to 66.065. I already told you the calculation of C is essentially is a trial and error procedure. So if you see what was the value of a C that we have assumed, it was 65 mm, and the actual computer value is 66. It is almost near to each other. It means that the CF is equal to 66 is acceptable to us. Now let us proceed directly to step 3. This is step 3 will check for the design compression resistance of the T-stub. Now we calculated the value of the effective bearing width. This means that we will be able to calculate what will be the effective dimensions of the bearing area. Obviously, the effective dimension B effective of this bearing area will be 2CF plus TF. Obviously, TF is the thickness of the flange and CF it is on each side of the bearing column flange, which means B effective will be 144.63. And L effective we know it is the width of the base plate, that is 350 mm here. So this means that FCRD, that means what will be the design compression resistance of the concrete, that is FCRD. We computed this as 857.77 kilonewton. Now we should ensure that the computed value of C is less than FCRD. For example, if you go back to the earlier calculations, we know that the value of C, that is a resultant compression that we calculated, it was 748 kilonewton. And we need to say that our concrete is able to take care of this force. Obviously, we find that the design compression resistance of the concrete, it is a 857, it is greater than C. So I provided a check over here, check T stub. If the computer value of C is less than FCRD, my check on the T stub bearing area is correct. Okay, otherwise it is not okay. So the result is good enough. That means our bearing widths are good enough to transmit compression C. So now let us proceed directly to step 4. Step 4 will provide you the check for the base plate thickness. And finally, we have got a step 5, that's a check for anchor bolts. Now, obviously, we know that the base plate thickness need to be computed based on the plastic moment of resistance of the plate. And this shall be calculated as per clause 624 of EN 199318. Now, we can calculate the plastic moment of resistance of the base plate as 0.25 into L effective into TP square into Fy by gamma MO. So this is on, please remember that this is on the consideration of a section modulus, plastic section modulus of TP square by 4, and we have got the yield stress of the base plate material as Fy. This means that we obtain for an effective length L effective plate the corresponding plastic moment of resistance MPLJRD is 19.4 kilonewton meter. Now we calculate the distance M. Distance M is nothing but it is the location of the anchor bolt measured from the face of the column, which is obtained as HA minus HC by 2. That is M equal to 50 mm. Now we know that our resultant anchor tension loads are located at a distance M equal to 50 mm from the face of the column, which means that in order that this plastic moment of resistance is not exceeded, we need to limit the bolt tensile load to a value FT1RD, which is computed as MPLRD by M, which is FT1RD 388.28 kilonewton. Please remember that this FT1RD is the maximum total tension in the anchor bolts, so that the plastic moment of resistance of the plate is not exceeded. And here we find that the corresponding bolt tensile load computed, it is less than the total tension T, which means that the check for the plate is okay. Now finally proceeding to the check for the anchor bolts, obviously we need to compute the tension resistance of the anchor bolts. which can be directly obtained from table 3.4 of EC318. FTRD is equal to K2 into FUB into AS by gamma M2. We, we have all the input values. So the corresponding FTRD is 203 kilonewton, and actual tension per bolt, it will be the total tension by 3, that is TB 116.312. This means that actual tension per bolt, that is 116 kilonewton, it is less than the value of what we call as the FTRD. So the check for the bolt I have written here, if if the actual tension in the bolt, that is TB 116.32, this is less than the tension resistance of the anchor bolt 203. So this means that the check for the bolt is okay. This means we computed all the checks, namely we have written down the equations of equilibrium, computed total C, total T, we computed the concrete resistance against bearing, compared it with the C, we computed the total tension with respect to both the plastic moment of resistance of the base plate and also from the consideration of the anchor bolts, and we found that both the base plate and the anchor bolts are sufficient to cater for the total tension T. So that is all for this presentation. Thanks a lot for listening.